For our next presenter, we have another person who lives in the Seattle region. He works for Microsoft, and he runs evaluation builds of Windows 10 in public. Please make welcome Steve Dower.
One of the major things that distinguishes humanity from animals is that we are tool makers. For every job we do, we design, we build, we optimize a specialized tool, whether that's a screwdriver for driving screws, an automatic defibrillator for bringing dead people back to life, or the various range of blades we have for everything from sushi through to navigating the jungle. And yet the tool that I bet most people, if you're carrying anything with you, is one of these. It's a multi-tool. It's not really optimized for any particular purpose, does a whole lot of things, but it comes in one convenient package that you can fold up and put in your pocket. And so it's the one you carry around. It is, by virtue of having everything you need to do and being present, the most powerful tool. We see a very similar thing with software. The software that we build and use looks a lot like tools. It is tools, specialized tools. We have a tool for searching files, downloading, uploading data, compression, decompression, encryption, decryption, and yet the tool that we love, since we're here, the tool that we love the most is Python, which is a whole lot more like a multi-tool than any individual tool. This is great. This is great for us. We have the most powerful tool, one convenient package, all the functionality we need to get a job done. But this is terrible for security. There's a phrase you'll hear once you start getting into information security called living off the land. This is a term that's used to describe what happens when an attacker manages to break into your machine, but they can't bring any tools with them, and so they're forced to use whatever you have already left on there. So they're going to use the same tools that you use to deploy code to run their code. They're going to use the same tools that you use for uploading and downloading to send their own data around, or worse, to send your data or your customer's data around. Can you imagine how thrilled attackers are when they get onto a machine and find a multi-tool there? That with one tool they can do everything? The risk here is that most of our security systems treat tools as the level of granularity. We can see them start, we can see them stop, we know how they were started, we know what they were told to do, we can force them to stop, we can stop them from starting in the first place, but we can't normally see any deeper inside. You see the whole tool or nothing at all. And so coupling this living off the land idea, which is extremely popular because it works well, with the idea that we have tools, the best thing you can do is to not leave your tools laying around. Don't deploy things that you aren't using. Don't leave them on the machine while you're not using them, because you're just making it easier for the attackers to do it. Which brings up a very, very important question. Is Python one of these essential tools? And should I be leaving it laying around? The answer, of course, is yes. It's absolutely essential. But is it going to stay that way? Imagine this scenario. You get broken into, you get hacked. And you discover this because your customer data shows up on a website for sale. And the security review finds out that the attackers got in because you had Python on that machine. They lived on that machine because you had Python on that machine, and they got it out, and the whole time you had no idea. Is Python really essential from the business's point of view if it's going to enable this? And how would you have caught it? I mean, sure, Python ran on the machine, but it does that all the time. That's the point. You're monitoring process starts, tool usage, but Python looks like a normal tool. It's fine. You're monitoring network connections, but the attackers came in through a developer's machine that connects anyway, so you didn't notice it. The point I'm getting at is when an attack looks like normal behavior, you can only see it if you're watching everything. To catch the abnormal when it looks normal, you have to be watching everything. And what this eventually turns into is you collect logging information from every single possible source you have, from your production machines, from everything connected to them, from everything connected to those, and you build yourself this massive, massive haystack of data to sift through to find that needle of an attacker is breaking in. And if that sounds impossible, good, you're awake, because that is completely infeasible. I want to take a brief sidestep to try and suggest a shift of mindset, because a lot of us will approach security initially by treating it as a high-value system surrounded by a wall. And as a defender, our job is to make sure that wall is impenetrable. And if an attacker breaches that wall, we've lost. Game over. And that's not the real mindset that we use these days. Because that wall is a million entry points that you have to protect. The attacker has to get lucky once to breach that wall, and they will. And if, in your mind, that's game over, you can't feasibly defend your system, because you have lost before you've begun. So we use a mindset called assume breach, where we assume they're going to get in. This is roughly the equivalent of having your wall, defending your wall, and putting motion detectors inside the wall as well, so that you know if someone's gotten in. That motion detector in our computer systems is what tools are being run, what things are they doing. And this is why Python is dangerous. Because from the tool point of view, it's a single tool. It's a black box. It has a secret life. Once it starts running, the things that it does don't show up in typical security logs for your systems. If someone borrows your screwdriver, goes away for an hour and comes back with it, what have they done? They've loosened something or they've tightened something. You basically know what they've done. Someone borrows your multi-tool, comes back an hour later, what have they done? You don't know. Maybe they've cut something, maybe they've eaten something, maybe they've trimmed their toenails in Starbucks. You don't know what they've done. Let's say you saw this show up in your logs. Curl is invoked. What has this done? If you understand the command line, this is enough information for you to know exactly what has been done here and figure out whether it's good or bad. Okay, if you saw this in your logs, you would probably go, yes, this is a bad thing. But what has it done? You don't know what it's done. And in fact, what it has done is it's decrypted that, which contains a URL, and it's downloaded more code, and it's decrypted that code and decompressed that code and executed that, and you're basically running arbitrary code on your machine, which has come off the internet. No one's seen it, there's no record of it, it's not been saved anywhere, and by the time you figure out the URL and go there, it's been taken down, and you have no idea. It might be something simpler. Again, this is arbitrary code execution. We're going to download a file from one of our own internal machines and execute that. And maybe this is how an attacker gets in the first place, because someone mistyped one letter and you've gone to the internet and downloaded arbitrary code and executed it on your machine. But this is all you see in the logs. Everything that Python has done behind this, you can't see. You don't know what it is. This is why Python is dangerous. This is why you should not allow Python on your machines. But Python is great. Python's probably the reason why your business is as successful as it is. It's almost certainly the reason you have the flexibility to get to market as quickly as you did. It's certainly the reason you have the maintainability to make changes as frequently as you do with confidence. It's the reason you have access to one of the biggest and fastest growing pools of new developers, new talent to hire. Python is your greatest strength, and disabling it is just not an option. But it doesn't have to be. Imagine this. Imagine when someone gets onto your machine and starts running Python, whether they're good or bad, instead of just seeing that it started, imagine that you also saw the thing that it did. Imagine this multi-tool was split up into a toolbox, and each individual tool is going to tell you what it did. The socket module is going to tell you everything it does. The ctypes module will tell you everything it does. Every call to os.system is going to tell you what it does. This turns Python from being a black box into an early warning system. Because at least for the immediate future, until they all hear about this talk, attackers are going to get onto your machine and try and run Python, especially on macOS, especially on Linux, where they can assume it's there. And you won't have any idea. Because what are your logs going to say? Oh, Python ran. But it ran thousands of times. And so you don't notice it amongst it, except because you've got additional information. It's telling you all the things it does. It's telling you every remote host it connects to, every piece of code it downloads and dynamically compiles, every file that it loads off the disk. You get red flags showing up everywhere. How could you miss it? Which leaves your attacker with a choice. Either they don't use Python, or they don't use the features of Python that are known to result in these logs and cripple themselves, or they wave their own red flags. The simple fact that they're coming in and using things that do not look like your application will let you know that they're there. Because you've upgraded to Python 3.8, and you've integrated it with your security infrastructure. So the feature that's in 3.8 that makes this possible is called auditing hooks. It came in through PEP 578, and it's essentially a side channel. It's an additional way that you can register a function to collect information about what Python is doing. And it looks something like this. Simplest possible example I can do while still using an F string. This is our callback hook. The arguments that come in are the name of the event and the arguments, very much like the name of the tool and the command line. And to register the hook, you can call this add audit hook function, which will add it to the list of hooks that get called on every event. The CPython runtime is already augmented with a number of hooks, so you'll get a lot of messages come out of here, and it's everything from imports to file access to network access, and includes some of the less common functionality that probably indicates someone is trying to hide from you. And third-party libraries can play as well. The sys.audit function is available to raise your own events, which means that whatever your framework does, if you have low-level functionality where it may be worth exposing that to someone who's interested in listening, you can do that with a function call. But if we're doing this for security purposes, we're probably not going to have much luck going to these We're not going to have much luck going to these malware authors and saying, hey, before you start running your malicious code in my machine, can you add this auditing hook for me? They're not going to do that. And so we're probably going to do it using native code. And so there is a C API for this as well. The hook, fairly similar. It takes the name as a string for easy comparison. The arguments come in as a tuple. And where we add it gets interesting. So we'll add it through the PySys add audit hook function. But we're calling that before Python actually starts running. So that PyBytes main function is the thing that starts Python. And we can add the hook before it even starts. And this makes sure that absolutely everything from the very earliest part of the Python runtime starting will be audited. It will give us information about what it does. This file can replace your Python binary completely. So you can use the standard Python, the standard libpython file with all the functionality in it. And your entry point, if this is the only entry point available, then you can guarantee that anyone who runs Python on your machine will be auditing events and you will be collecting them. There's one other API, which most operating systems have a way to distinguish loading executable code off the disk that they're going to run versus plain old data. Python previously did not, and now it does. We have a function called open code, which is used anytime we're going to open a file that may contain executable code. And the reason you do this is it avoids some timing attacks compared to simply looking at audit hooks. But essentially, we'll call import. That's going to find a .py file, and it will call our hook. The hook's going to open the file, do some verification. I'll show an example of that later on. And then return a file-like object when it's checked that it's OK, or it's going to fail and say you can't use this file. Again, this is an API we can call before Python starts to make sure that every single file load through all of the initialization can be logged or verified, whatever we intend to do. And so we have 6 new APIs. 6 new APIs that will let us add auditing hooks, raise auditing events, and verify code file opens, which helps ensure that Python no longer keeps any secrets. Every time it runs, we'll now get to see everything that comes from the ctypes module, everything that comes from the socket module, every remote address, every interaction with the user will be audited in a way that we can collect, review separately, and respond to. Okay, I've been very abstract. I'm going to get into 3 concrete examples now. There are 3 main scenarios that you would use these for from a security point of view. There's a number of useful scenarios for other purposes. From a security point of view, you generally want to do 3 things. You're either going to enable trusted code to run, which is essentially block everything and allow good things. You're going to want to prevent known bad code from running, which is we assume everything's OK and these things are not allowed to run. And the third is log everything. So I'm going to go through 3 concrete implementations of connecting to these services. I am going to do it on Windows. There's 2 reasons for that. 3 reasons for that. The third is that I work for Microsoft. The first is that the screenshots are prettier. The second is that these are all built into the operating system, and there's one obvious way to do it. Which means if I come to Windows and say, what is the right way to verify that this file is allowed to run, there's one obvious way to do it. And if you are actually going to implement these, then you really are going to map them against these services. The link at the bottom of all my slides goes to a much longer version of this, written up as a white paper, many more examples. And of course, everything that I talk about here can be implemented on whatever platform you're on. The challenge is it's going to vary by what you need it to do. And as the upstream core team, we're not going to make that decision for you. It's just not a priority to figure out if we're on this platform, we should integrate with these services. If we're on this platform, we should integrate with that. So these hooks are about enabling you to do it in your context for your purposes. So the first example is allowing trusted code to run. And for this, I'm going to use Windows Defender Application Control. As I said, the basic idea here is that we assume that nothing is allowed to run, and we create a configuration that says, actually, these things are allowed to run. And it ends up looking kind of like this until you've enabled things. It's an operating system configuration, which means we're going to fill out a really big configuration file that is XML. We're actually going to use a tool to generate it, realistically, because it gets very long. But the idea is that this configuration file gets given to the OS, and then the OS will enforce lockdown policy against certain files. By default, it's going to do that for binaries, executables. It won't do it for Python source files. And so we have to do a little bit of work in Python using the open code hook to enable this for Python source files. So there are a couple of types of rules here. This is far from a complete file. But there are file rules. You can allow or deny certain files based on their name, their full path, version numbers, hashes. There's a variety of ways to explicitly enable and disable things in configuration, but the interesting one is this signing certificate. Now, Windows has a system for code signing files, cryptographically signing files, that lets you put the public key in this file, keep the private key somewhere secure, and sign things before they get deployed. And then anything that Windows can verify is signed by this key will be allowed to run, which means you can update your deployment without having to redo the operating system configuration. If you're interested in how secure this configuration is, come talk to me later. It'll take about half an hour to explain, but it's a real pain to change this configuration. So if you can deploy files that are signed correctly, you'll have a much more manageable time. And you'll notice this certificate is labeled Python Software Foundation. Everything in the official distributions of Python is signed. All the binaries, all the non-binaries, all the Python source files are code signed in that distribution, which means by putting this key in here, I'm able to use the official distribution plus the extra hook to enable policy for files. Here's the code. This is a helper function that I'm going to call from an open code hook. I've already extracted values out of the Python objects because I don't want to go through all that 3 times. But I've got the file name, and I've got an open handle to the file. So this is an open code hook. I need to return an open file object. I'll pack those into a structure and ask the kernel for the lockdown policy. I don't have to know where the configuration file is. I don't have to configure it myself. This is an operating system managed feature. And if the OS says there's no configuration at all, it's going to say go ahead and run the file. So this is theoretically something that could be in the core Python distribution for Windows. But again, this is not one of our priorities on the core team right now. It will come back and say, yes, you should enforce lockdown. in which case we don't allow the file. Otherwise, we'll allow it. And when you run, this is the kind of thing you see. So the first input is going to import the collections module. That's in the standard distribution. That's been signed in a way that Windows is able to verify and say this file is allowed. The second example, I've actually shadowed and modified the random module. So it's got malicious code in it. But because it doesn't match the signature that was in the official distribution, it's blocked. It's just not allowed to run. And so in this way, by default, things that are not approved for use will not be allowed to run on your system. Things that are allowed to run. And with the open code hook, we're able to extend that to Python source files and not just the ones that only the operating system supports by default. Second example is preventing known bad code. This is the kind of thing you do when a certain variety of ransomware gets really big and everyone knows what it looks like, but it's still spreading really quick, and you just want to prevent it running on your system. And so you have an anti-malware scanner or something along those lines, which are available for all platforms these days. And you'll update the signatures. The advantage of this is you haven't had to redeploy your application. You haven't had to reconfigure your application or your operating system, because it's regularly updating itself anyway, and so you have a very smooth process to just stop an attack in its tracks. For this example, we're going to use the anti-malware scan interface. This is important for Python because Python can dynamically compile and execute code, and malware scanners typically only see what's written to disk. And so an attacker who will come in with encrypted code that the scanner doesn't recognize, decrypt it, and execute it can bypass all of these checks. The anti-malware scan interface is an operating system API that will forward in-memory buffers to the malware scanner and get the response back. It doesn't require knowing what scanner is enabled. It doesn't require that you have a scanner enabled, though it's not very useful without one. But it lets you connect up between an application that has something in memory that needs to be scanned and a scanner that's able to tell you if it's malware or not. Again, I have another helper function, but I'll show you the actual call to it on the next slide. This one is for the compile audit hook. And when the compile audit hook is called, we get the code that's been compiled and the file name. And we pass those into this function. There's a little bit of setup and context around this one, but it's still quite straightforward. The code is just passed in as a buffer. This is probably a UTF-8 string, but we didn't actually ask. We got a pointer to it, and we got the size of it. And the scanner can figure that out. The scanner can figure out if the encoding is suspicious or not. But it is at the point where it's about to be compiled. If this is not valid Python code now, the next step is an exception, because the compile function is not going to work. So any decryption that's been done to make it back into real Python code has already been completed, and we can see that. And if the result says, hey, this is malware, then we're going to block it and we're not going to run it. The call from the hook looks like this. We'll check the event. We're only handling the compile event. And the arguments come in as a tuple. There's a really convenient pyarg parse tuple function that can be used to pull apart these messages to get the data that's being passed in. And then we can pass that to our helper function. And again, if that's blocked, we'll raise an exception rather than opening the file. When run, it looks like this. I have imported a module and called a function to get my test string, because if you put this test string in the file, then you don't even get this far, because the malware scanner detects it. And so I've actually obfuscated my own code so I can do this test. This test string is recognized by Windows Defender, but there are other test strings you can use for other platforms. And I'm just going to eval it. And normally this would, obviously it's not Python code, it would give you weird errors. But because we've added this detection, we're able to intercept that and run the scan. And it will say this is being blocked. This is not allowed to run. And as a bonus, our malware scan is going to give us a notification. In a networked environment, it's going to send that notification somewhere central. So as the administrator of your network, you will know that malware is starting to appear on your systems, and you can look into it. Big red flag, letting you know that someone is doing something they shouldn't be on your machine. And the third example is logging. Log everything. You need to log everything. Just log it, all of it. But the pushback to that, particularly from engineering, is, isn't that going to hurt performance? And The short answer is yes, it will hurt performance. Any request that is logging everything that it does is going to take a little longer than one that doesn't. On the other hand, any business that is not logging enough information to detect and diagnose and clear out an attack before their customer data is stolen and you get sent out of business by the cost of a GDPR violation, if you'd prefer that, I'd say you're optimizing for the wrong case. Luckily, if you use a proper logging system, proper logging infrastructure, you will bypass a lot of the overhead. So the Windows event log, like most logging systems, including syslog, is going to use deferred formatting to help ensure that the overheads of logging all this information are as low as possible. Again, we get a nice big XML file. Here's the interesting part. We have a template for an event which defines the data that it's going to take in. A tool later is going to turn this into generated code, so we have a simple function call that will take these arguments and very efficiently copy them into the log. Because we're doing deferred formatting, these are kept as raw data. And so we specify the in type, which essentially means const star in this case. The out type says, here's how to process it on the way out. And the message string goes somewhere else completely. It doesn't end up in your code. It's used entirely to render the output to anyone who's reading this. And the format substitutions get applied at that point to give you a coherent message. And in the event viewer, it looks like this. We have an operational log, which means expected events, things that regularly happen. And when we look at an event, we'll see that it has been formatted together. And we have compiled code, we know the file it's come from, and we see the code itself. We have a complete log of everything that's run in our Python, in our system. And it's been brought into one place. In code, this looks very much like the other ones. As I said, these are designed to be simple to integrate with, but in general, most audit hook connectors should be relatively simple. These are not places you want to do huge amounts of work. You want to minimize it. For this hook, again, we only care about the compile event. If we have a different event, we're going to bail out as quick as we can. And then logging the event is a call to that generated code with the raw data types. We'll do processing, we'll do formatting later on. And because it's integrated with the operating system, you get access to all the functionality that comes with that service. And this is going to apply to all services that are doing this kind of logging, because everyone needs this functionality. Encrypted logs, write-only logs, log forwarding, sending all of the events to one central location, additional metadata, you don't have to worry about. You've done your integration with the one obvious logging infrastructure for your platform, and that will give you all the information you need. I keep saying you will do this, and that's because you will. It's very important that you enable what makes sense for your context. You are the one who's going to have to read these logs, to analyze these logs, to see what's happening, to detect when something unexpected is going on. There's no point enabling this if you're not prepared to do that. You need to know who your opponent is in this. And if you think you don't have any opponents, then consider that if you're deploying to any cloud system and happen to be in the same data center as someone who does have opponents, you are now a potential pathway to get into their system. That's a real thing. Also consider that some malware is non-discriminatory. It's generally believed at this point that the NotPetya ransomware from a few years back was a targeted attack against specific Ukrainian companies that within 24 hours had infected people all around the world. It was a targeted attack that still got you. You have opponents. Are you ready for them? Auditing hooks in Python will allow you to take control. The decision is not between do we allow Python or do we disallow Python. The option is whether you are watching it. And you don't have to be held hostage by open source development priorities. You have the ability to enable this integration now, to collect this data now, to track the attacks that are coming against you now, and to respond, to prevent them, and to prevent significant damage as a result. The tools that you deploy to your systems will either support and protect you and your users, or they'll be used against you by your attackers. Don't leave tools lying around, but better yet, turn them into early warning systems that support you and that protect your users. Let Python 3.8 be your early warning system. Make your attackers wave the red flag themselves. Tell your teams that It's time to upgrade. Thank you.
Thank you, Steve.